And today is my talk, which I named Random Notes, Quantum Physics and Complex and Hyperspace. So let me share a screen. Okay, this is my screen, and this is my presentation. Okay, so what is the main purpose of this talk? I want to present one of the possible ideas how to model the dynamics of long polymer. Why I am talking about dynamics? Because the evolution of long linear polymers has some interesting properties which is hard to model. Actually, what is the reason why we have to pay attention to the dynamics of long polymers? Because of they have a random shape. This random shape is caused by the flexibility of chemical bonds between monomers, which are parts of polymer. On the picture, you see one monomer, and it occurs that neighboring monomers can be related to this monomer via chemical bonds in several positions. These positions are taken from the from physics. They give a minima to energy of connection. And it occurs that this position randomly changes due to intrinsic reasons and due to the interaction with the media. Since the number of monomers is relatively large, like 10 in 5 or 6 power, then even if the angle changes very on the very small value for every bond, for every pair of monomers, you can imagine that all polymer gets a very complicated shape. Also, it is known, for example, for DNA, that due to the double spiral structure, DNA can cross itself. On the picture, I just give you some imagination how it looks like. The lines from the spiral are disconnecting, but subsequently, and then glue up again, because as we know, the DNA consists of complementary monomers. So one can see that DNA can organize some knots. And the last phenomena, but very important, is folding phenomena, which arise due to van der Waals force. These forces are not very strong, but on the very short distance between monomers from different parts of polymers, then they became to walk, and it can happen that pairs of such monomers, as you see on the picture, remains to be close after they began to interact with this van der Waals force remains to be close all the time of evolution. Then another pair arise and so on. And finally, you see the roughly speaking, packet knots, how the DNA looks. So these three features, three properties of dynamics of polymers is very hard to model. This leads to the following, not phenomena, but following situation. We have a very long list of literature from mathematics, from applications devoted to structure of polymers, to mathematical models of polymer, and one can here check the well-known books of Bolthausen, van der Hollander, Remco van der Hofstad, and others devoted to the mathematical model of polymers. But there are almost no literature devoted to dynamic of law. Today I want to propose you some ideas how to model this. This is what I said, and here is the references. Van der Hollander random polymers, Bolthausen construction of three-dimensional polymer measure. This is a well-known paper. And Giacomin random polymer models. Let me say again that most of these models do not evolve in time and are based on a Wiener process. Why they are based on the Wiener process? Because we see the polymer, and as we have seen it change randomly its shape. So we suppose that we have a stationary case, and then we have a distribution, probability distribution on this in the space of curves, or in the space of closed curves on polygonal lines. And people always think that maybe trajectories of Wiener process are good example of such polymer. Why? The reason is that the bonds in polymer, which are not neighbors and have some distance along the polymer, move like independent. So one can say that, okay, let us take the process with independent increments but continuous. This is Wiener process, and then let us consider its trajectories as a model of polymers. There are a lot of problems there. For example, this paper of Bolthausen was initiated by these problems related to excluded volume effect. We cannot put two monomers in the same place in the space, but Wiener trajectory, for example, in dimension 2, can intersect itself even several times in one point. So maybe Simanjek and Evans proposed some procedure how to exclude or punish some trajectories which have self-intersections. So people build polymer measure starting from the Wiener process distribution. But As I say, this is like stationary case where there are no any evolution with the time. The main problem which I want to discuss today is to build the model which evolves over the time, can change its topological type, and has the following effect. I think that almost a year ago, I proposed here the model which evolves over the time and can change its topological type. It was constructed by with the following idea. We just have a random field, isotropic Gaussian smooth random field, and consider the image under the action of the field is three-dimensional, and consider the image under action of this field of the moving circle, for example. In this way, we obtained a closed random curve, which changes its topological type in the random moments of the time, not in deterministic moments. It has no self-intersection, but there was no folding effect in those models. Since then, I tried different approaches to include folding effect here. One was based on the equation with interaction, where this van der Waals force was included, like interaction force between particles. But it occurs that under this approach, we have sufficiently fast shrinking of the knot. I tried different shapes of the van der Waals force, and it occurs that it is not very appropriate, at least on those examples which I tried. Maybe it can be continued in this direction, but now I want to propose to you a different idea, and this idea is based on the construction of the motion of one particle in the random media in RD, where the noise is complicated. So if I want to summarize in few words what I want to propose to you, this is the construction where the particles will interact using the surrounding noise. So let us start. The motion of one particle in the random media in RD usually is described by the Ito stochastic differential equation, where we always say that A is the coefficient which is responsible for description of the external force which is acting on our particle, and B dW is the description of random perturbation. So one can continue and asking about the set of interacting particles in the random media. Here you see the equation with the interaction, which we discussed in this seminar a lot of times. I just recall that here mu t is a mass distribution of all particles, and you see that mu t is an image of the initial mass distribution under the flow xt. Xut is corresponding to the motion of the particle which start from the point u at time 0. And here you see a new element comparatively to the diffusion equation. This W capital, which is Wiener Schmidt on RD multiply on 0 plus infinity. W capital can be viewed as a family of independent Wiener processes. We constructed as follows. If EK is an orthonormal basis in L2 RD, and we define WK, W small k T as such an integral from W capital, then one can define coefficient decay, and finally, this term with W capital occurs to be just infinite sum of usual stochastic differential of Wiener processes. Moreover, these Wiener processes occurs to be independent. So one can say that maybe this is just some artificial mathematical construction. It is enough to have one Wiener processes. Why we need too much, even in infinite set of Wiener processes? But it is important. The difference between this differential bxt dw small for one particle and this sum bk xut dwkt in case of the large family of particles is a possibility of complicated correlation. For example, one can calculate the correlation between martingale paths of xu1 and xu2 particles which start from u1 and u2 at time t, and of course it is equal to such sum of products, so scalar product of two infinite sequences. And on other language it is equal to the such integral from the function psi, which was introduced in the equation with interaction. And then, for example, one cannot get this correlation in the form exponent minus norm xu1t minus xu2t squared dt using finite number of Wiener. So if we want to have freedom to consider arbitrary positively definite function like a correlation function between instant correlation function between our particles, we definitely need infinite number of Wiener processes. This explains us why we consider this Gaussian random measure or infinite number of Wiener processes in the model. By the way, my colleague and friend, unfortunately he died, Peter Kotelenius, has a very deep motivation from physics why we need infinite number of Wiener process using trying to model the moving particles in the random media. So we have seen that we have two sources of interaction between particles. One is the force. You see in the coefficient A dependence on mass distribution of all particles. And coefficient A can be, for example, of the following kind, as you see here. In this case, J is like a force which exists between two particles placed at the points xut and xvt. And by the way, it was my idea with van der Waals, with the model of van der Waals force. And in this case, I tried J of different shape. of different shape, but the results were non-sufficient. And another source of interaction is the correlation due to influence of random media. You see, one can get the following, even for example, the following correlation between the particles. So one can expect that choosing the kernel psi, which is responsible for interaction of our particles with the media, one can get, for example, the following effect. The close particles can remain to be close due to the high correlation between their motions. This is the idea of the so we use the second mechanism, and now let us try to find such psi. Why I am saying trying to find appropriate psi? Because we are thinking, we are speaking about the evolution of the particles in random media, evolution of the long polymer in random media, and of course we can write something artificial, but I think that we have to find such functions from some dynamics, maybe intrinsic dynamics. And so let me propose few examples how one can organize such interaction with the random media. So H be a real separable Hilbert space, psi1, psi2, psi3 be independent Gaussian white noises in the tensor product H multiply on L2 0 plus infinity. One can consider the elements of this tensor product like H-valued functions with the following scalar. And then one can define the integral with the white noise, and you see, suppose that psi, which belongs C1, R3 multiply on 0 plus infinity and with values in H, be such that we have the following. For all U and P, the norm of Hilbert norm of psi is equal to 1. Now define this the process YUT is U plus the integral from psi US psi ds. Here you recognize exactly the same expression which was considered before when we discussed the equation with interaction and Gaussian measure with independent increments, W capital. So now let us define for smooth closed curve gamma 0 in R3 its image under this mapping Y. This is gamma 0 T. And gamma T describes the evolution of random mode in this talk. So this is the model of the evolution. Of course, all properties which we want from this model are hidden in the choice of the functions psi. One remark, which is very important. This process YUT, let us see again on its definition, here is it, is not a solution to stochastic differential equation. Is not a solution. You see, in the right-hand side, there are no any Y. Is not a solution to stochastic differential equation. Why? I choose the following Y. Y small. because y small may not be a diffeomorphism. You remember the one of the uh, beginning and main theorems from ordinary stochastic differential equation and from stochastic differential equation that when we have good coefficients, then solution is a flow of diffeomorphism. So I want to exclude this. Why? Because to be a flow of diffeomorphism for our random maps y means that our random node cannot change its topological shape. We have no this phenomenon of self-crossing. Yeah, if we have the flow of diffeomorphism. So this is the reason why I'm considering this y. Now let us consider several examples. Maybe when I wrote this norm psi ut equal to 1, maybe you recall Schrödinger equation. So let us consider as a source of our functions y a Schrödinger equation. Let us identify complex plane C with the real space R2 in natural way, define H like this, and here is R3 with Lebesgue measure and R2 valid. So consider now Schrödinger equation with the initial condition phi 0 from our H and such that norm of phi 0 is equal to 1. Then it is well known that the solution also will have a norm equal to 1. And moreover, this solution has a good structure from the view of physics, but I will say not very good for us. The solution is like phi t equal ut multiply phi 0, where ut is a unitary semigroup. Because the Laplace plus some potential is unitary operator. So we have a unitary semigroup. It's self-adjoint, excuse me, operator. So this is unitary semigroup. And if we now have this F, which belongs C1 R3H and define CUT equal UT from FU, then what we will have? The correlation does not change. So if we start from the product FU1 and FU2, then we have the same. Yeah, correlation does not change. So let us discuss another approach, again from quantum physics. This is so-called Koopman von Neumann mechanics. The idea of Koopman von Neumann was to use the same language as in quantum physics, like Schrödinger equation, wave functions, and so on, to apply it to usual mechanics. In usual mechanics, we have the motion which is described by the ordinary differential equation of the first order. So we have Hamiltonian, we have two say coordinates, impulse and coordinate, and for these two coordinates, they can be three-dimensional. We just get the equation with the derivative from Hamiltonian. They propose to do the same, but with the functions. And now define H as L2R6 with Lebesgue measure, and again R2 as values. And consider this R6, as I said, to is related to the product R3 multiplied by R3 and corresponds to idea that the wave function now depends on two arguments, position Q and impulse P. Evolution equation in Koopman one name and dynamics looks like this. And you can see they wrote with imaginary unit in both sides, in order to make it much more close to Schrödinger equation. But it occurs that if we consider complex valued functions, this operator L, which is this is operator of the first order, yeah? But now it is Hermitian. And then, as exactly in example 1, Phi is now again a solution is again a image under unitary semigroup, and we can again construct the functions psi ut, define processes y, and it occurs that these processes are Wiener processes. Every particle looks like moves like Brownian motion, but they have fixed instant correlation. So we consider next example, which is related to Markov semigroup dynamics. Let PT UV belongs to R3 be a transition density semigroup. So we have some, for example, good diffusion process in R3, and then we know that it has transition density, and this is its semigroup. Defined with phi ut, this is just a square root of this density. It is in L2, and in this case, Wiener processes YU are correlated. And the distance between psi ut and psi vt now is well known in probability. It is a Hellinger distance between corresponding probability distributions. And this distance can be compared with distance in total variation, with Wasserstein distance, and we have theorems which says us that sometimes this process, this diffusion process, can be ergodic. Yes, and in this case, one can expect that the processes Y became to be more and more correlated over time. So in this case, the instant correlation between particles can change. Now the next example 4. This is simply a differential equation in Hilbert space. Consider the function h from h to h, which is continuously differential with bounded derivatives and has the property that for all h belongs to h, the scalar product h is equal to 0. Then the solution, using the method f defines the function psi ut as a solution to Cauchy problem for such stochastic ordinary differential equation in Hilbert space. Due to the property of our function h, if we start from the element which has not equal to 1, it remains to be equal to 1, so we have an equation on the sphere in the Hilbert space. The behavioral correlation between the processes YU depend on stability properties of the proposed differential equation, and one can propose different examples where A has, for example, some attractors on the unit sphere in Hilbert space. Then definitely we have the effect, that correlation between different the particles in our initial space R3 will increase. This is the model of the motion. Now let's see on the properties of the obtained random node. As we remember, we define gamma t as an image under the mapping y, and the natural question, the first natural question is the following: when gamma t is a random node, so when gamma t has no self-intersection with probability 1. By the way, there are a lot of polymers in our surrounding life, like natural proteins, DNA, also artificial polymers, which has self-intersection, has much more complicated structure. But if we are speaking about DNA, for example, it has no self-intersection, and somebody can ask why we consider not, why it is closed. But let me answer that there are some very small creatures, like which are consisted like from the one клетка. Which are very primitive, but the DNA
Cell.
yes, thank you, Yana. The DNA is closed. It is actually a knot. So we consider, suppose we consider primitive DNA. So we want to understand when gamma has no. So let us consider general abstract situation. Let zeta be a three-dimensional Gaussian white noise in H. Suppose that gamma 0 is this is a function which is 2 times continuously differentiable and periodic on the interval 0, 1 in R3. This gamma 0 like parameterization of some good curve. And suppose that this curve has no self-intersection. Now consider some mapping from R3 to H, which is injection, and which is also C2. And suppose that gamma S is simply a product of this f gamma small 0s with three-dimensional white noise. This is a Gaussian random node. Then, of course, the definition of a Gaussian random node can be formulated simply, much more simply, as a smooth periodic R-surveilled Gaussian process. But we use the structure of f and gamma 0 to formulate our state. So you remember, gamma 0 has no self-intersection, f is a smooth injection, and then with probability 1, kappa has no self. The idea of proof is more or less the same as I proposed here on this seminar a year ago, and is based on the calculation by 2 different ways the local time of self-intersection. So let us consider this 2 intervals, sub-intervals of 0, 1, which are disjoint. And then expectation of delta function from the difference gamma t2 minus gamma t1 is finite. Let me recall you what does it what does it mean. Delta function is now the following limit in the weak sense of the indicator function of a small ball near origin, around origin, and divided on the volume of this ball. The volume of this ball is proportional to epsilon in power 3. Then this local time of self-intersection with delta function inside of the integral is nothing else than the limit. The corresponding integrals when we substitute this approximating sequence instead of delta function. But moreover, we can proceed more formally and more easy. Some random vector has a density, this is our case, has a density, smooth density, then the expectation of, we don't need to define the delta function from this random vector. We just need to define the expectation in this formula. The expectation is just value at the point in our case of this density. That's all. So it is easy now to check that due to the these intervals a, b, and c are distinct, and properties of our functions f and gamma 0, this integral is finite. But now let us see what happens if we consider really smooth curve in some self-intersection point. Then the time which this difference x2 t2 minus t1 span near zero, near points of self-intersection, is more can be estimated from above, from below by c divided by epsilon, and you see this contradicts to this, yeah. So if with positive probability we satisfy this inequality, then this expectation must go up. This is the idea, and since then gamma is a naught. Now we know that this is a naught, but what is its topological type? Again, a year ago I proved.
Andrey Anatolyevich, could you please explain one more time? If epsilon is small, this time, this inequality, if epsilon is small, the time when kappa T2 is close to kappa T1 probably is small also. Maybe
yes,
C times epsilon squared.
Yes, it is small also. It is small also. Oh, excuse me. Of course, this epsilon must be. Thank you. It must be here. Yeah. Then everything is okay. When we,
yes, sure. And we have epsilon cubed in denominator, so
exactly. Yes, exactly. Thank you.
And I have one more question. So kappa of S is a Gaussian curve. It is a Gaussian process, and you use this property.
You use it heavily here. When we check that this integral is finite. We don't need to have precise covariance. We don't. We just understand that this covariance in the denominator has a norm of the difference between this kappa between this f gamma 0 in different points, and f is injection, gamma 0 is also intersection, and we have smoothness.
Is it correct that if you have a Gaussian process,
yes,
with non-degenerate covariance, then
yes,
then it has no intersection?
More or less, yes, but we need some technical.
And smooth covariance.
Yeah, yes. If it is smooth, yes, surely, yes, exactly. Exactly.
Thanks.
Exactly. This is the idea, actually. This is the idea. Then gamma is a knot, then what can be its topological type? Because for those partial model which I proposed on this seminar a year ago, I was able to prove that gamma t can have an arbitrary topological type with positive probability. So the question is, for arbitrary non-random K, does event gamma, by the way, that this have the same topological type? This is event. It was proved. Have the probability not one, of course. This is a mistake, but positive, greater than zero. Yeah, this is a question. And it occurs that here the crucial property which allows us to prove this is the following. Is the sort of distribution of kappa and kappa 2 prime, second derivative, in this is equal or not to all space of continuous periodic functions. It was crucial. It is more or less reasonable because actually what we want to do, we just have some deterministic node, and it is closed curve, so it is continuous periodic curve, function from 0, 1 to R3. And then in the small neighborhood of this curve, deterministic curve, we want to find trajectory of our kappa. Of course, we have to be careful. This is a reason why I am saying about this kappa prime, 2 prime, because it can happen, for example, that kappa is in this small neighborhood, but it also has a very small knot on itself, which are placed in this neighborhood of deterministic knot. This is not not a good case for us. So to avoid this, we actually need to approximate not the function itself, deterministic function, but its second derivative. So this is the reason why I'm speaking now about second derivative. But nevertheless, since the coordinates are independent, it is enough to consider the one coordinate kappa 1, and here we approach a very, in my opinion, very interesting problem from Hilbert space geometry. Let me formulate. Consider kappa 1. Note that F is injection and continuous. Denote K. This is an image of gamma 0. It is trivial that K is compact. And it is well known that if we have injection, which is continuous and so on, this function f minus 1 also is continuous. Consequently, the following question arises. When here is a question completely from the one point, from the serial function process, from another point, from geometry of compacts in Hilbert space. When the compact set in Hilbert space is such that, first, the isonormal process, scalar product with the Gaussian white noise, has a continuous modification. And secondly, when the distribution of this process has a support which is dense in CK. You see? So this is a problem. And as we will see in the as we will see further, this is not very easy. But it formulated very shortly and nicely. when the compact is such that the isonormal process on this compact has support which is equal to the space of all continuous functions on CK. The first part of question, when isonormal process has continuous modification, was answered by me in our joint article with Mikhail Popov in 2014. Namely, it was proved that isonormal process has a continuous modification if and only if K can be embedded in some Hilbert-Schmidt brick. Now suppose that gamma 0 is smooth and F is smooth, then kappa has continuous modification. Hence, F of gamma 0 is a subset of some Hilbert-Schmidt brick, by the way. So the smooth image of any smooth curve from R3 to Hilbert space can be embedded in some Hilbert-Schmidt brick. Now consider examples and counterexamples to the second part of the question. So we will consider compacts when the support of isonormal process coincide with CK or let me say to you that we can forget about all probability theory. Why? Because it is known that the support of isonormal process is the closure of the following set. This is just a linear or scalar products with the function from H. This set QH, the closure of this set give us support of isonormal process. So now we have the purely deterministic formulation. When the closure of this set considered as a functions on the compact K is equal to all set of continuous functions on our compact K. Let me show you different examples. Examples when it is the answer is positive, and examples when answer is negative. Negative. Take E which belongs to H and norm of T equal 1, define K like this one. Yeah. Then CK can be naturally identified with C01, but the set of QH now is one dimensional. All function of the form they contains all function of the form QT equal AT, or some possible A from R. So we see here that on a good compact, our set of function QH is very pure. The same happens if dimension of the linear span of K is less than infinity. So if K is embedded in finite dimensional subspace, then trivially dimension of QH is less than infinity, and we cannot expect any good answer. So this is not a let us consider another example. Example 2. Consider the space L201 as an H and define K as a following compact. This is a set of indicators of intervals 0 t when indexed by t, and now t is from 1/2 to 1. Then being identified with the subset C 1/2 1, the set QH contains C1, and then it is dense in all C 1/2 1, and we have good answer. By the way, now this isometric isonormal process is simply Wiener process. Yeah, it's simply Wiener process. So What we can learn from these two examples. The compact K must be locally infinite dimensional, even locally, because if we consider CK, this is a good metric space, so one can construct a continuous head for any ball in K. So for any neighborhood, we can do this. We can see we must have the infinite infinite dimensions of this neighborhood. Also, its points must be separated from the complements of the definition. If the support of isonormal process is equal to Ck, we call this case non-degenerate. Remark here, Andrey, as you asked before, the same definition can be formulated as a property of continuous Gaussian process itself. Yeah, we don't want Hilbert.
Does this notion close to local non-determinism?
Exactly, I will say about this. Yeah, exactly. Continuous centered Gaussian process eta u on the compact space x rho is non-degenerate if we have this property. Yeah. This no property is very close to the local non-deterministic property for Gaussian random fields. Because what is the one of possible formulation of local non-deterministic property? This is a condition on the conditional variance of Gaussian process at the point u, when we know everything outside of the small neighborhood of this parameter. And Gaussian local non-determinism in different variants looks like this quantity depend on epsilon, like we have some epsilon and some power, or some other functions depending on epsilon, estimating this from below. And here you see we say here that points must be separated from its complements, from the complements of their neighborhood. It means that the orthogonal complement of the point to the closure of the linear span of all points outside of its neighborhood must be non-zero. This orthogonal complement for isonormal process is nothing else than the conditional variance. So at least we need that it is positive. Unfortunately, I am feeling that it is very close to sufficient. But at that moment, I cannot prove. But I will propose to you some sufficient condition for random fields. Yeah. Suppose that H is equal to L2R, and the function P belongs to L2RD and has Fourier transform which is not equal to 0 at all points of RD. Then the following random field, we just do the following. We take this P and move it on the space. And if, by the way, maybe it was firstly systematically considered by Julian Anatolyevich Rozanov in his devoted to partial differential equation with the random noise. He considered this Gaussian white noise in L2RD as a generalized function and considered equation with them in sense of generalized function. So in sense of usual deterministic partial differential equation. So here we have a convolution, yeah, of this function p. Then this process eta is non-degenerated on every compact subset. The idea of proof: let K be a compact subset of RD. If eta u is not non-degenerate, then must exist a finite measure mu on K such that this random variable is equal to 0. Because of support of Gaussian distribution is always linear subspace. If it is not coincide with the all Ck, then we must have the such continuous functional on Ck, which vanishes on support, and from other side is non-trivial. This is exactly what I wrote, because continuous functional in our case are just finite measures, finite of finite variance. Then for all v from RD we have such expectation equal to 0. Then it means that for all v from RD such equality holds, but this is nothing else than double convolution p, p, and mu. And hence we have that Fourier transform of p is not equal to 0 totally, then mu Fourier transform of mu must be equal to 0, and so mu must be equal to 0. This is about so we can propose a lot of such functions when our process y ut will have a different topological shape type. Let me say. Now let us say something about force. Now suppose that the function psi us are sufficiently smooth, have bounded derivatives, and there exists positive function c such that it is square integrate, and for all uv r3 we have that this difference has a norm which is less or equal than norm u minus v multiplied on ct. Here symbol k in brackets means number of derivatives. So for function psi itself, for function for the first derivative, for the second derivative, and this is with respect to the space argument u. So we have symbol 1 near psi. Then for any fixed s, there exists the following limit. If we shift our gamma t on the one its point, it by the way it does not matter on which one. Then we just get a limit in probability in space of periodic continuous functions. So what does it mean? It means that our curve freezes at infinity. Maybe okay, you will see the picture how it looks like. Freezes at infinity. Remark. The first one. In case when psi is, I just repeat, in case when psi square root from transition density, the norm is a Hellinger distance between. This distance can be compared with a total variation distance and other metrics between probability distribution. Hence, one can look at ergodic processes, ergodic transition densities, and an example. When we have a good mixing, for example, Stein-Uhlenbeck is so, we have this property. The second, technical condition 2 can be relaxed. Of course, here we can have some much more complicated continuity from U and V, which measure close distance between U and V. But this condition allows us to prove the statement relatively easy. So this is a statement, and the idea of the proof is the following. Consider just one coordinate, it is enough, yes? Then there exists a finite limit of the joint of the characteristic of the difference. This is due to our supposition. Then one can use Knight's theorem. The difference is a martingale, and it is continuous martingale, one-dimensional. So we can apply a Knight's theorem and say that it is a Brownian motion from its characteristic, some Brownian motion from its characteristic, but characteristic is finite. Yeah? So, oh, here is another bracket. Here must be another bracket. Oh, here another bracket. Okay, so then we have a limit. Now we have a folding effect. Moreover, our knot freeze finally and move like a solid body in the space. Of course, it moves because every particle, as we have seen, moves like Brownian moves. Every particle. But now they freeze and became to move parallel. So this list just about finishing proof. We have a point-wise convergence, but the estimation for the difference of this psi which we have, this one condition 2 give us the uniform continuity which leads to desired convergence. The last remark which I want to say that the same construction can be applied to the interacting Markov chains. And in this case, even one can use instead of wave functions which are defined like elements from L2, RD, and so on, one can consider vectors. So one can consider finite dimensional Gaussian white noise and get some interacting Markov chains. But for me, it was interesting to get a continuous picture. And now let me show the picture how this model works. This model was created for me by my PhD student Katerina Kustaryova, who is very good not only in mathematics but in handling of different computer involved problems. So here in this model, we are working with the kernels psi, which are related exactly to Ornstein-Uhlenbeck process, as you mentioned. And of course, the Brownian continuous Brownian motion was substituted by Gaussian random walk with very small diffusion. Like as far as I remember, like 1/100 is diffusion. So let's see how it evolves. You see, firstly, the path of the knot moves independent, more or less. We cannot say independently, but they move in different direction. They organize some complicated structure. You see here, this is okay. So this is a time when part of nodes can do whatever they want. But then all construction began to freeze. And now you can see that more or less it began to move like a solid body. By the way, the picture which we get here is very close to pictures of proteins, of DNAs in real photo from different investigations. So I hope that we will do some statistical
Andrey Anatolyevich, so is it correct that the scale is changing? So this curve is bigger and bigger. So the range of this curve.
I supposing to say about this, yes, but it became to be, but finally this process of the growth is stopped. And maybe it is not too hard to understand why. Because one can even find the distribution. This is actually this is a like question for nearest investigation, I suppose, to do this, and it is not too difficult because what is like maximal data? This is a maxima of difference. So this is the maxima of Gaussian process, yes. And if we use Knight theorem, yeah, more or less this is a maxima of Brownian motion on some fixed interval, yeah, up to this time infinity. Of course, this is just more or less, but you see here it freezes, and then that's all. Maybe it is good to just let me I speed the time. Yeah, you see, it moves like a solid body, and here is its final shape. Yeah. So yes, it grows, but the growth is controlled. We checked this because, of course, this is not a first attempt. We spent probably 2 weeks or even greater trying to find appropriate parameters in Ornstein-Uhlenbeck density, in the size of diffusion, and so on. So there are a lot. By the way, we model Gaussian noise too to define Ornstein-Uhlenbeck. So to define these Brownian motions, yeah. So there are a lot of parameters in this model, and we spent a lot of time just try to choose appropriate parameters. But this picture looks much more realistic comparatively to the pictures which we get when, as I said in the beginning of the talk, we considered van der Waals force in the interaction term with dt. Then it shrink our knot very very heavy, and the length of the knot change, but now it is controllable. But in those case, it change it tends to zero. Yeah. Okay. So this is all what I wanted to present to you. Thank you for attention. Here is a reference to my papers devoted, which I mentioned. And thank you for your attention, and special thanks to Katerina for this nice modeling. Maybe somebody have questions.
I have one question about support.
Mhm, mhm.
You explained that support of the process is all phase of nodes,
Yes, yes.
but you used second derivative, and I
Yes.
understand that. Okay, if you have some curve, but
Mhm.
there are many. There may be a lot of small nodes in a neighborhood.
Exactly. Yes, exactly. Yes, exactly. As I said, we need control to the second derivative. So all which we said here must be repeated relatively to the second derivative.
So you need a theorem about support of a pair, eta and second derivative.
Actually, you see, if you okay, yes, but if you have a statement about support of second derivative, then this is a periodic case.
Then you integrate 2 times and
Yes, and it was in this stuff what was surprising for me that we need the secondary, not the second derivative, in order to avoid this small notice, so small loops inside. Yeah.
but you demand only 2 times
Yes.
continuous differentiability of your functions.
Oh, yes, this is a technical.
No, I mean maybe you have maybe you need more.
Yeah, surely you are right. To get, I consider here just a case of like without derivative. Of course, if we need to have to have a second derivative of the process, we need something more from the our function. Yeah, but I always kept in mind this example with density of diffusion process, yes, ergodic diffusion process, and in this case, for good coefficient, it is even infinitely many.
Could you please recall the definition of this random curve that you simulated?
It is.
I mean, was it like y of the circle at time t?
Yes, exactly. Let me here we have, but only one moment. I will turn in this way, turn my screen because now I can write easily on it. So, what was the model? Firstly, we start from the circle in R3, and the
So this
circle
was
is,
gamma 0.
yes, it is gamma 0, and it is like A cosine S, A sine S, and 0 at the third point. Yeah. Now let us define U. Let us define Y. We have to make some integration. Yes, we have. So how we model this noise? We take sufficiently large number M, sufficiently small delta. This is like this one. Delta is like this one, and then but positive, and then consider it a cube. A cube. This is like minus m 1 over delta and m 1 over delta cube. Then in this cube we considered points like k over k delta plus oh, excuse me, minus m This is minus this one.
Andrey, my question was not about numerical scheme, but about true.
Yes, the density which we use, this is I simplify Nulenbeck like this one. This was how standard Gaussian density, but with this minus u multiplied here is
this function psi was square root of density.
Yes.
Okay, I see.
Yeah, this was the case. This also is matter of question, and I think that, as I said, we will do some statistical investigations in order to understand what can be our parameters in reality.
So if this function c is square integrable from 0 to infinity, then maybe this case is not too much far from t in a compact in 0, 1 after some change of variables. Is it correct?
Too much far from what?
No, I mean, you consider limits as t tends to infinity.
Yes.
But your function, your control of your Lipschitz constant is integrable.
Yes.
So maybe after some reparameterization of time, you can just consider finite interval 0, 1.
But you see, this is this conclusion we can make only on the difference. As I said, every particle still persists Brownian motion. So all this curve will finally move like one solid body, slightly moving.
I see. So this body is rotating.
Yes, and moving like one Brownian particles along the space.
Thanks.
By the way, this also gives us hope that actually we can consider a lot of such random curves simultaneously, because it is known that for polymer in some fluid, we have not three-phase state like solid, gas, and fluid, but we have five. And this five-phase state depends exactly on the shape of this long polymer. If you have so-called people in physics, they always think that complexity is something random. So they say this is something like statistical, I don't know English what, статистический клубок. This is one. Another one is much more packet knot, and another one is just long lines, and another one happens with these long lines are placed parallelly, and so on. So this effect that finally we move like a solid body give us a hope that we can model not only one polymer.
Is this related to colloidal stuff Kotellenis wrote about?
I think yes, but of course, actually, in the beginning, I said that the ideas to use Wiener sheet, so this infinite number was derived by Peter from the physics. So yes, it is related. Yeah.
Mhm. I have a question about statistical properties. So you are intending to like obtain some results. So last time you spoke about this, you spoke also about like quantitative characteristics of such caps, like the mean number of nodes as
Yes, yes,
integral.
yes. So in this model, this is just my my plan actually for the next week. Yeah.
But you need to develop like algorithms for calculating them from
Yes,
approximations.
yes. I think that we did something with Katerina already, but with such not very interesting topological characteristic like diameter. Katerina, am I right?
Yes, you're right.
Yeah, but not for this model, for previous, yeah?
Previous, yes, not for this.
Yes, not for this, for previous, and it was bad sign that those model was shrinking
Yes.
up to point, yeah. Okay.
Thank you, because it seems like a problem of itself, like developing efficient and verified algorithms for such models for numerical approximations.
You know, by the way, for algorithm, I think that even physicists do this. They use this Möbius energy. Actually, it can be calculated. Oh, by the way, for previous model we calculated it. And as we discussed, Möbius energy can help us to estimate from above the complexity of the node. So yes, of course, this is a plan to do. A very good plan.
I see. Thank you for explanation.
Okay, if there are no other questions, then let me stop sharing the screen and ask Georgi who will be the next speaker.
The next speaker will be Katerina Glyenina.
I see. This is some filtration problem.
Filtration problem for SD with interaction. Yes.
Okay, good. Okay, then thanks everybody and see you next week. Bye.
Thank you. Thank
Bye.
you. Bye.
Goodbye.
Bye.